Hello, my name is Daniel Helbing. I'm from the University of Salzburg in Austria, and I will present some examples of the work I did together with my colleague Lorena Abad on erosion feature mapping using knowledge-based and data-driven methods. When I talk about knowledge-based methods, I mean that an expert like me integrates data in a classification workflow and sets the parameters and thresholds for the classification based on his assessment. And when I talk about data-driven erosion feature mapping approaches, I mean that computer algorithms use the input data and calculate based on the specific algorithms the output. The first example is about earth flow mapping in the Tirol catchment, following up Andrew's talk. Here we developed a semi-automated detection method of potential earth flow locations. That's important to mention. I will come back to that later. We used an object-based image analysis approach, and as for all the examples, both DM data and optical data. First step in setting up the workflow for detecting potential earth flow locations was identifying specific characteristics that can be derived from aerial photography and DM data. So we did this based on a discussion during the meeting a few years ago, based on literature review, based on experiences we gathered in the field, and came up with several characteristics, which are shown down here. For example, the existence of rushes in the bare ground, especially at the toe of the landslide, the moderate slope, the connection to streams, and other features that could be derived from remote sensing data. This information was then integrated in a knowledge-based classification workflow, which started with combining optical and DM data, then performing a segmentation, that means grouping neighboring pixels into homogeneous objects. As a next step, classifying these objects on a final level, meaning classifying, for example, the rushes and the bare ground, then grouping these objects step by step to finally come up with potential earth flow locations. And here are some results of this mapping exercise. So we compared these potential earth flows to manual mapping we performed as well. And here we can say that we matched about 87% of the reference earth flow polygons. However, as you can see in these examples on the right-hand side, in yellow, this is the manual mapping. In orange, this is our automated mapping. There are quite some differences in the exact delineation of the earth flow boundaries. However, here it's important to mention that also the manual mapping is quite uncertain. So we have to be very careful with this comparison with numbers. In addition, we identified quite a lot of additional potential earth flow locations, such as shown here. This was detected because the data we used showed the characteristics as we identified before. This might be an earth flow. This could be an older earth flow which is not active anymore. This could be an area that is susceptible to earth flows, but there's need further verification if it's really an earth flow or an active earth flow. Coming to the second example, which now goes away from a knowledge-based approach rather to a data-driven approach. We've used deep learning. Deep learning is a method in artificial intelligence which allows us to extract complex features automatically from different data. And here we did a gully characterization and detection using historical reference data in the Mankato forest. We used data available from Marden et al. From 6 points in time, starting from 1939 to 1997, as input for training the deep learning model, because the deep learning model heavily depends on the input data which you have. This data is a great input data. However, we faced several issues with this because there are quite some co-registration errors. So they do not spatially match because of the input data that used for this manual mapping. As you see, for example, here, this is the same gully, but the spatial match over time is not given in the reference data. And we tried to partially correct this, but we couldn't fully do it because there were no regular shifts, but the internal distortions in the data. So it's very, very hard to fully correct these issues. Nevertheless, we used this data as input data for the deep learning and checked what is possible to create out of that. And by grouping these single Earth flows into, or based on topological relationships, we could estimate at least the evolution of one Earth, Gully, still at the first Gullies, of course, of one Gully complex. The next step was to derive different terrain derivatives from the DM data and compare the characteristics for basins with gullies and without gullies. This is shown on the top here, where we have, for example, curvature, length slope vector, terrain roughness index, and so on. And we try to find out these terrain derivatives which are more characteristic for subbasins that show gullies than for subbasins without gullies. Based on a statistical assessment, we selected then the most suitable terrain derivatives input for the deep learning. Here you see the result. On the right-hand side, we have the training and testing data in red and orange. And on the left-hand side, we have the results of the deep learning approach. So I think the pattern as such looks quite good. We have here the certain locations, the gullies detected as we can see them in the reference data. However, there are some issues involved with this mapping, as I indicated already before, especially the time difference between the historical reference data and the DM data. The more recent DM data we used is an issue because these delineations do not really match the recent data. And this creates problems for the algorithm. And also when looking close at the classification results, the delineations of the gullies differ quite a lot from the reference data. Anyway, I think at least the overall pattern looks quite good. But we are still working on that and trying to improve this mapping approach. And the third example, and probably the most relevant one, here we did some cliff and gully detection in the Varroa catchment using both approaches, a data-driven approach called deep learning mask RCNN and a knowledge-based Abaya approach. We selected from this larger study area several grid cells for training and testing and validation, which are shown here. Here are some examples shown. These three examples were primarily analyzed. And then we did again a statistical assessment of terrain derivatives. So we calculated about 30 terrain derivatives and assessed how do random features compare to erosion features and how do gullies compare to cliffs. What you can see here, we find quite some significant differences between erosion features and non-erosion features, but gullies and cliffs are not so easy to differentiate. And based on this assessment and several tests, we selected then some input layers and with the deep learning mapping. The second approach here was this knowledge-based Abaya mapping approach, where we followed again similar approach as just described, creating image objects, then classifying these image objects, combining spectral, spatial, and morphological characteristics. As one zoom into this, the one subset of the analysis area, which looks pretty good. So when we have in black and red the reference data, the manual mapping, and in yellow and turquoise our automated mapping, we see quite a good match between the reference data and our mapping. Same as in these examples. However, it's quite dependent on the expert knowledge which you put into the into setting up the classification workflow, and also the especially the differentiation of cliffs and gullies turned out to be quite challenging. And now looking at both examples or the results from both methods, we can see that overall the deep learning performed a little bit better, but there's no big difference. But when looking at the different erosion features, we see for the cliffs, the deep learning resulted in higher accuracy values, while for the gullies, the Abaya approach resulted in higher accuracy values. What is interesting in general, we mapped much more features than were existing in the reference data. These are the one and false positives likely, but on the other hand, I think there are quite some features missing in the reference data. For example, as shown in these two examples here. We mapped here features with both with the buyer and the data-driven approach, and this matched pretty well, but these were not present in the reference data. So meaning that such an approach or such approaches could be used for updating and complementing existing inventories. And then finally, two short examples for additional work we did, which is also somewhat related to the topic of landslides and river interaction. It's about mapping and monitoring landslide and lakes. Here we use time series of satellite-based remote sensing data, especially Sentinel-2 images, and did on the one an automated analysis at regional scale with an data-driven method and a knowledge-based analysis on local scale. For the regional scale analysis, we performed the mapping of monitoring of landslide and lakes after the Kaikoura earthquake. And for this purpose, we set up a classification workflow in the Google Earth engine, which allowed us to access all the Sentinel-2 imagery which are in there without downloading them and setting up a very performant processing workflow. So this runs fully automatically and can be applied to different study areas. And as a result, we came up here with a suggestion of how to categorize the landslide and lakes into different categories based on their spatial temporal evolution, meaning constant, increasing, decreasing variant. This final example, there was recently a master student at our department who I supported with this work and who did quite some nice work in using also Sentinel-2 time series from 10 points in time. Here I showed just 3, for example, monitoring the evolution of the Kaikoura landslide, the landslide and lakes. And this is quite interesting because the landslide developed over time, and also the lake appeared and disappeared. And here we applied an bio workflow to monitor the changes, both features between 2017 and 2021. And we did some visualization in 3D to better communicate and show the changes. Okay, so to conclude, I think reliable analysis methods are needed to better understand the spatial temporal occurrence of erosion features. This can be used in different ways, for example, for improved representation of erosion processes for catchment sediment budget models. It can be helpful for implementing effective erosion mitigation measures for supporting disaster risk reduction. The special remote sensing and the newly appearing advanced image analysis techniques provide great opportunities for erosion feature mapping and monitoring. However, this is also dependent on the data availability. So with having more data, for example, more high resolution EM data over time, multi-temporal EM data over time would further contribute to this exercises. This would be helpful, but it allows also the integration of different kinds of data, optical data, DM data, also radar data. And this application of different methods is also possible, integrating expert knowledge using modern data-driven methods. And finally, quick remark on the international collaboration, because Chris asked me for doing that. So I think from our point of view, it was very, very interesting to be part of this great project. And I think the collaboration was very fruitful. It allowed us to develop technologies which we also applied in other areas, mainly in Europe, of course, in a very interesting study area, and to perform joint research. And that's to increase our general science understanding and further developing technologies. And I think there was also a mutual benefit by exchanging knowledge. So for me, it was very interesting to get the knowledge from the local experts and integrate this in the mapping approaches, because that's a very relevant aspect to exchange methods and ideas. We also had the chance to perform joint fieldwork and produce joint publications, while some of them are still ongoing. Thank you.